Right, I hope you are seeing my screen. And I think I can start. Just let me know if you don't see my screen. So I will start here. And so I'll start with a brief agenda of today's talk. So I'll start introducing what is model interpretability and Captum library for model interpretability. Then I will move on to different types of perturbation and gradient-based attribution algorithms, followed by concept-based model interpretability and model robustness techniques. And lastly, we will recap the talk, talking about the future directions. So what is model interpretability? So you probably have heard different definitions about model interpretability, and you have also probably heard about explainability and how people use those two terms interchangeably. So for the sake of this presentation, we would like to define interpretability as the ability to describe AI model internals and their predictions in human understandable terms. And we will use different types of techniques to be able to explain and interpret the predictions in human understandable terms. So we'll use both terms interpretability and explainability interchangeably. So why do we care about it? We care about model interpretability because it helps us to increase the transparency of our models. It helps us to better understand how our models reason, why, for example, our models make misclassification or misprediction, and how we could potentially improve it. And the better we understand our models, the more likely it is that we will improve it, and the more likely it is that we will be able to do cutting-edge research. So for these reasons, in 2019, we introduced an open source library called Captum that is based on PyTorch. The library helps model developers to interpret the predictions of their models using different techniques and algorithms, and it has three main characteristics. So the first characteristic that I would like to highlight is that the library is multimodal. It works with PyTorch models that take input from different sources, whether it's image, text, audio, video, structural or unstructural input, and combine those different modalities. Second is the unified nature of a library allows us to combine and use together different algorithms and techniques and different ways of interpreting and explaining models, for example, how we could use attribution in combination of robustness or concept-based interpretability. And lastly, the library is designed for ease of use, so that the users can use it with a couple lines of code. So one of the core components of Captum library that we have is the attribution algorithms. That's we have a number of gradient and perturbation-based attribution algorithms that help us to interpret our model internals or input features. And we categorize them into three big groups. So first group is a primary attribution. These methods help us to attribute output predictions to the inputs of the model. In this case, we use integrated gradient algorithm to attribute the target class target 0 to the input features, feature 0 to feature 2. The second group of attribution algorithms help us to attribute the output predictions to all neurons in an internal layer. These are called the layer attribution methods. And here we show how we could use one of our layer attribution methods, such as layer conductance, to attribute the output target prediction, target 0, to all neurons in an internal layer. And the third group is the neuron importance algorithms. This group of algorithms help us to attribute an individual neuron in the model or an aggregation of the neurons to the inputs of the model. For example, you could imagine we have a gradient shap or a neuron gradient shap or a neuron saliency that we attribute to the input features of our model. And here we showed an example of it. So as we can see, there are a number of algorithms that we could use using the same signature to understand the importance of input features or internal neurons, and they all follow the same signature. So we create an instance of an algorithm, pass the predict function, then call attribute the inputs of the model and other necessary arguments. So besides that three categories that I described, there are two big types of attribution algorithms. One is a gradient-based attribution methods and another perturbation-based. So we'll start with the gradient-based attribution methods. So gradient itself describes the infinitesimal change in the input that changes the output. Hence, the gradient explains the output change by the means of the saddle input perturbations. And in the world of PyTorch, we can compute gradients very quickly for many of our models or all of our models using forward and backward passes. So some of the limitations of gradient methods are the gradients can be noisy. They aren't necessarily faithful to the model output. And in order to reduce that noise, we could sample in the neighborhood of our input X that we want to explain, and then compute the gradients for those inputs and aggregate them. That will help us to stabilize the explanation, but this will be costly because we will have to do sample in the neighborhood of our input X. So one of the famous approaches for gradient-based methods is integrated gradients, which is an advancement or a better approach of doing gradient-based methods rather than just computing local gradient for a given input point. So integrated gradients computes the gradient along the path from baseline x0 to input x. So in this case, I have an example of an image. The baseline is a black image. It could be any uninformative input or any input you would think to compare to the original input in order to draw conclusions, what is exactly important for that prediction. And in this case, in order to compute the integral, we would need to use a Riemann sum or Gauss-Lagrange or other approximations, and we would need to sample, find examples along this line that will help us to approximate the great integral. So for the images, this looks like something like blurring the image, right? So integrated gradient basically computes the gradients, aggregate the gradients from a black image to this given image. It means what it will take us to go from a black image to the real image in terms of a gradient change for my prediction. So as you could imagine, finding good baselines can be very challenging. So in this case, I have a black image, but you can imagine you could have white image or noisy image. And this is still an open research area. Also, this method does not take into account the correlation and interactions of our features. And this is something that we want to do in advance and understand the correlation and interactions, or use more advanced techniques or improvements of integrated gradients that will help us to take that into account. So another type of attribution methods is perturbation-based methods. So compared to gradient-based methods, perturbation-based methods look into a substantial change, not an infinitesimal change the way the gradients do, but a substantial change in the input that perturbs the output. For example, if you ablate a feature, if you permute features. So a feature ablation, permutation, or Shapley values are great examples of it. So some of the limitations of these methods is that perturbing each input and computing the changes in output of our function can be very time consuming. Also, the perturbed input might no longer belong to our train and dataset manifold. It could also affect or break the interaction relationships between certain features. And that's why when we use this type of methods, it's important to understand the relationship between different features. And when we perturb and ablate or permute features, we do it in a group using a mask. So I'll demonstrate one of the algorithms called Shapley value, which is adapted from cooperative game theory, and it measures expected marginal contribution of each feature for a given sample and prediction. So let's imagine that we have a game setting, a collision, where we have 3 players, Alice, Bob, and Mary, that are participating in a game. And there is a total of $20 that we want to distribute across our players, Alice, Bob, and Mary. So in a very fair setting, the more Bob contributes, the more a player contributes into the game, the more money they will get from the payout. So this is a fair estimation how we can fairly distribute this payout between different players, so that the game is fair. So in this case, if we take this to a setting of a feature importance and our model, our features are the players and the total payout is our prediction. So we want to know how much those features contributed to that, to the game, to the prediction. So let's look into a specific example. Let's say we have a regression model that takes 3 different inputs, the age of the house, number of rooms, and location, and predicts the price of the house. In this specific case, we have a house that is 40 years old, has 3 rooms, is located in San Francisco downtown, and it costs $500,000. So the goal is to understand what are the contributions of each of those 3 features for the prediction. To do that, let's assign feature IDs to these features and look all possible permutations and ordering that these features could enter the game, could enter the prediction scenario, and what are all possible permutations. After we list all possible permutations, and in this case, it's 6 because we have 3 features, we start adding those features into the model in the ordering specified in the permutation. So we will start from the first ordering. And this, in the very beginning, we don't have any features, we don't have any players, and we compute our function output when features are not present, are empty. Then the first feature arrives, which is the age. We add it to the game, compute feature, functions output for that feature. And then we compute functions output when the next feature, the number of rooms, enters. And lastly, when the location enters, we compute the function output as well. So after the first permutation, we compute the contributions of each permutation, of each of these features for the first permutation. And that represents the differences of function output after the feature arrives and before that. And this way, we get the contribution score for each feature after the first permutation. And then we continue that for the next permutation. For the next permutation, we again start from empty setting. In this permutation, the first feature that arrives is number of rooms. So number of rooms arrives, and then the age arrives, and then the location arrives. Again, we compute the contribution based on this setting and this permutation. The differences right after and before the feature arrived in the game. We can continue this for all 6 permutations, and Shapley value represents the sum of all these contributions across all those permutations normalized by the number of permutations, which is, in this case, 6. So this equation formally explains what I showed in my previous slide. So the contribution of feature xi represents the function differences right after the feature entered and before the feature entered, summarized across all our permutation and divided by the number of all possible permutations. So as you can imagine, this method has limitations. There are exponential number of feature permutations. So how do we solve this problem? We solve it by approximating Shapley values instead of calculating exact Shapley values. And there are methods called, for example, kernel Shap. Kernel Shap approximates Shapley values by computing the conditional expectations of a contributions instead of the marginal expectations. Shapley value sampling will help us to sample random k permutations instead of taking into account all permutations. So as you could see, many of these methods sometimes require runtime, compute, and a memory. And there is a trade-off that we need to make between the memory usage and the compute. And when we start perturbing our inputs, it's important to take into consideration that we could batch it. And that's something that Captum takes into account by batching our inputs and accelerating the computations. Apart from that, we can take advantage of the GPU's data parallels, distributed data parallels, and model parallels to reduce the compute time even further. So this slide summarizes all algorithms that we have in Captum library. On my left side of the slide, we can see the algorithms that help us to attribute output predictions or internal neurons or aggregations of internal neurons to the inputs of our model. On our right side, we see algorithms that help us to attribute output predictions to all neurons in an internal layer. Gradient-based methods are highlighted in purple, perturbation ones in pink, and there are two other algorithms that do not belong to any of those big groups of attribution that we highlight in dark blue. So some of these methods are baseline, and it's good to start with something baseline like saliency, input times gradient, or layer activations. And some of these methods are well known for convolutional networks or in a computer vision communities such as guided GradCam or occlusion, but our implementation is more generic, and you can apply it to any type of model. If the algorithm requires ConvNet, then you want to make sure that your model has a convolution and it's appropriate to apply to your model. So now, after we talk about different types of attribution algorithms, the question is, how do we evaluate them? How do we understand the goodness of those attribution algorithms? So we all know that looking visually at attributions could be create confusion, or different people have their subjective opinion what is important in our input. So there are no perfect quantitative and qualitative metrics to evaluate the attribution. So I'll talk about infidelity and sensitivity max, which can help to a certain extent to quantify how reasonable those attribution scores are. So sensitivity max measures the sensitivity of our explanations or attributions in this case to saddle input perturbations. So we basically sample in the neighborhood our input X. You could imagine we just add white noise by taking a radius, a predefined radius that the user specified from an L infinity ball, and then we use Monte Carlo based approximation to identify how sensitive is model explanation to the input perturbation. The second method is called infidelity, and infidelity measures the distance and using mean squared error between dot product of our input perturbation and explanation and the differences of a predictor function at its input and a perturbed input. And this is a property that many attribution algorithms share, such as integrated gradients or deep lived. So I explained a little bit about the attribution methods. Now I'd like to talk a little bit about other techniques such as robustness metrics and attacks. So robustness attacks help us to understand models' vulnerability to saddle input perturbations. They're white and black box attacks, and here I demonstrate FGSM white box attacks that slightly perturbed our input and fooled our model from predicting electric locomotive to a warthog. These algorithms are also very simple to use in Captum library. You could import them the same way you do attribution algorithms, just from the robust package. And then when you call perturb on the algorithm by passing the minimum perturbation step size and the target, you could construct the perturbed input, and of course you could visualize it and see how the model behave when you slightly perturb the input. In this case, we could see that this specific use case, electric locomotive, is being predicted as a plow. So you could also imagine of using these perturbation techniques and perturbing inputs to create counterfactual examples. And you could use it in combination with feature importance score or an attribution score. Attribution score would tell you what is the most important in your input, and you could attack those portions, those patches in your input. For example, what will take your model to predict a streetcar instead of an electric locomotive? As we could see, these black patches will help us to explain that. So now let's talk a little bit about another area that we invested in Captum, that's concept-based model interpretability. So concept-based model interpretability helps us to explain our models using high-level concepts. So for example, we have here a concept of strap, or we have a concept of random image, and the goal is to measure models' sensitivity to high-level concepts. So one of the well-known algorithms from this field is testing with concept activation vectors, which is a two-step procedure. In the first step, we generate concept activation vectors. We basically try to understand what type of concepts do different layers in our models learn. So for that layer, we train a classifier, in this case, a linear classifier that distinguishes and learns the hyperplanes that divide those concepts from each other. In this case, we could see that the hyperplane, we could see that concept activation vector is the one that is orthogonal to our hyperplane that divides our straps concepts from a random concept and is pointing towards that concept. So after generating this concept vector for this specific layer, we can then start explain prediction for specific examples. For example, if we want to explain the prediction for the zebra images, what we could do is during our forward and backward pass, we could compute the attribution score, the feature importance score for each neuron in this layer. And then we could perform a dot product, compute a similarity score, and see how much aligned is this attribution score with this CAV concept vector. And the more aligned it is, the higher would be my TCAV score. That means the higher would be my concept score, a concept contribution for this specific prediction. So here is an example how we could use it in Captum library. We have here, we could import the concept class and the TCAV class. Then we have to provide the data loaders or data sets for the concepts. In this case, you could specify the data iterator. Then you'll create an instance of a TCAV class, passing model layers, and then the images for which we would like to perform the attribution. In this case, we could see on the y-axis that's the TCAV score, and the x-axis are the layers. We can see that we received a TCAV score for straps almost equal to 1 across all layers, which means this is pretty high score that the straps contributed to zebra prediction, whereas the random concept did not contribute to the prediction. So to summarize, so I talked about a number of gradient perturbation-based attribution algorithms, which can help us to understand the important features, neurons, and layers in our models. Also two evaluation metrics in fidelity and sensitivity max that can help us to evaluate the goodness to a certain extent of those explanations, robustness attacks and metrics, and concept-based interpretability. I'd like to invite you to try out our library and report issues and questions that you have. We certainly plan to extend the library in the future, add support for influential instances, model comparison, optimization-based visualizations, model debugging, and embedding visualization tools. And with this, I will wrap up, and Josh will continue the presentation from here.
Splendid. Thanks, Narina. Okay, I need to share a thing. Bear with me for one moment. Oops. Splendid. How does this look?
Good.
Fabulous. Okay, so hi, I'm Josh Rubin. I'm on the data science team at Fiddler, and this is part 2 of the complex model tasks and operationalization bit. So I'll talk more about the operationalization part. So I like to show this slide. So modern machine learning frameworks are extremely flexible, and model developers build powerful models in unique form factors. And it's sort of impossible to anticipate what amazing things they'll come up with. So, you know, here's a few frameworks. So tools like Captum that Narina just told you about provide powerful interpretability for these complex model types. In the case of Captum, it's for the PyTorch framework. But what does it mean to operationalize interpretability across an enterprise? So I've heard hints of some of these same concepts all day at the panel. So it seems like we're all tapped into some sort of increasing collective understanding that there's some important components that are needed. So one is that you need to make insights available to all stakeholders. 2 is that standardizing model sharing workflows is important. So that means that models need to, get from one person to another in a well-defined way, and ad hoc processes get tricky. And so this is basically what I'll talk about for the next 3 slides or so. But the idea is that these problems are addressed with a centralized model performance management platform, MPM. So I'll talk about it generally, that concept, for a couple of slides. At some point, it'll kind of morph into Fiddler, and I apologize if this turns into a little bit of a Fiddler plug, but that's obviously the lens that I think about this problem in. And then finally, whatever this thing is, it needs to support the kinds of complex model scenarios that Narina just told you about. So we've seen Captum do this. And so I'll finish this with an example of using Captum and Fiddler together. And I'll describe it at least in broad strokes. It won't be super technical. Super. Okay, so how do we make interpretability available to stakeholders? So I write this here: empowering all stakeholders to evaluate whether a model is serving its intended purpose is a responsible AI best practice. It might even sort of be responsible AI. The more of the human beings that care about how a model is working, the better you're able to determine whether it's serving its purpose or not. So, model developers love to work in whatever tools they like to work in. Often that's a Jupyter notebook. They'll pick a modeling library. They'll pick some tooling. But there's generally lots of other stakeholders involved, right? So there may be, in some scenarios, there's a model validator who's different than a model developer, who receives a model and is responsible for kicking the tires and making sure it's doing the thing that the developer intended. They may like an explainability GUI that lets them interact with the model, explore its dependencies, look at point and global explanations. They may also work in their own analysis notebook, and it's really helpful to them if they can interact with that model in a standard way. There's MLOps engineers. They're going to want to have a monitoring GUI where they can set thresholds, they can look at charts for drifts. There are executives who are model responsibles, governance and compliance people. They want something like a dashboard view that gives them a bird's eye view over how the models are doing. They also tend to care about standard report generation. So, there's some sort of hard record of the way a model performs and how it's been validated. There's also application domain specialists. So I'm super interested in this category. This is essentially people who work in various business verticals who aren't data scientists, but receive predictions from ML models to do their jobs. So some examples could be like a fraud auditor or a career counselor who works at a company that matches resumes with job roles, or a physician who's working in a medical setting who's using a machine learning model to make care decisions. Those people all benefit from understanding why the model made the decision that it did and not just its prediction. They want explainability integrated into their own workflows. So that's an API integration. If you give them that, they're also better able to communicate back to model developers when something is inconsistent with their domain expertise. So it's kind of human in the loop and sort of completing that feedback loop. So moving interpretability from model development notebooks to a centralized diagnostic explanation serving platform It makes insights available in a role-appropriate format. All right, now standardizing ML workflow. So within large organizations, it's common to leave the choice of ML tooling to the developer, to the model developer. Because of this, like, portfolios often contain models that are constructed from a wide variety of frameworks, tools, and customization. And so basically every model ends up being represented in a different way, requires different tools to set up. So here's the pain point, right? Model developer has data files with various splits. They may store stuff in CSV files or pick your file format. There's various kinds of model artifacts depending on the kind of framework. There are dependencies, environment setup, custom tooling, diagnostics, interpretability, notebooks. And for every model, the other stakeholders have to receive that bunch of stuff. There's often a negotiation and a kind of communication that has to happen for how to spin up that model and for that stakeholder to interact with it in the way that they need to. So it's kind of a bummer for the downstream recipient. And it introduces a huge amount of inefficiency into organizations that have a lot of models, a lot of devs, and a lot of stakeholders. So what's the solution here? So here's our model developer. She has a whole bunch of different tooling she pulls from. If she wraps her model and encapsulates the specifics and sends that to a model performance management platform, those models become standardized in how other stakeholders interact with them. And that streamlines a lot of things. So standardized serving and interface to models, data, and explanation. That's user interface and API. It streamlines downstream validation and monitoring workflows. And then everybody is way happier. So sometimes we get this question, like, what's the value proposition for the model developer in this model performance management thing? Because they're perfectly happy in their notebooks. And I think it reads something like this: like, a small investment in standard tooling, the NPM, it leads to repeatable cross-functional workflows for enterprise scale model portfolios. So essentially, that's the model developer's responsibility in order to be a responsible part of this AI ecosystem. It's to expose their models in a standard way. Cool. So that's my pitch for NPM and operationalization. Let's talk briefly about this case study idea. So the case study is to ingest a complex model with a framework-specific explainer into Fiddler. So the model I'm going to tell you about is a bank churn classifier. It's trying to determine whether or not a particular bank customer is going to leave the bank. Binary classifier. Its inputs are multimodal, which means that it has different input shapes that are coming into it, basically. So it'll have a dense vector of bank relationship features. I'll show you more in a minute. And then there's also going to be a sequential input that describes a series of events that have occurred in that customer's bank history, which comes through as a sort of a matrix inputs. It's a sequence of event vectors. So the model in this case is built in PyTorch. And the model developer is going to use Captum for interpretability in their own workflow. And I'll talk in a minute about why they might want to do such a thing. And then we'll incorporate both the model and the Captum integrated gradients feature attributions into Fiddler's NPM platform via this custom explanation mechanism that we've developed. And so you might ask yourself, like, why does something like Fiddler and NPM need a custom explanation mechanism? So, we talk about the explainability we provide with our product. Fiddler's got several built-in explanation algorithms, including integrated gradients, which is implemented in a very general way that can accommodate a lot of different, it's very framework agnostic. So why would you want to bring a custom explainer along? And so here's a few reasons. So one is the model developer might instrument a model for explainability early in the life cycle for feature engineering, for debugging. So reuse that work. If you've gone to the trouble to instrument your model, no need to replicate. A framework-specific implementation of an algorithm can sometimes be easier to instrument than the model-agnostic version that the NPM platform provides. So Captum, for example, knows all the details of how PyTorch works. And so it takes some of the onus of exposing that details off of the model developer. There also might be a special purpose algorithm, maybe not in this case, but in some cases that's particularly use case appropriate or efficient. So if you have one of those, it's important that you're able to bring it. Cool. Okay, so here's the model. You have two inputs. One is a vector of credit score, age, tenure with the bank, balance. I think there's also a number of products that comes up later. And then there's also this matrix, which is a sequence of events that are time ordered. And those events have a type. So it's a thing like made a deposit, made a withdrawal, open an account, close an account, how long ago that happened, whether there's a monetary value associated with that. Inside of the model, that gets processed by an LSTM, a recurrent unit, that turns it into a dense vector, which can be joined to those initial features. And then it goes through a fully connected classification network to make a probability. Cool. Okay, so as a model developer, I do my work in my Python notebook. I train this simple multimodal model like this. It's simple structurally, but the fact that it's multimodal presents challenges for explainability and for presenting that data at the end. So I'm using Jupyter and PyTorch, and here you can see here's my model. Oops. You have an LSTM that is processing that sequence. It gets concatenated somewhere here with a dense vector, and then that's fed into this simple sequential model. And it outputs a value between 0 and 1. And so we train this thing, and model developers like to see you get an accuracy that increases as you train. And so you get some good lift out of including this complex multimodal input space. So that's all great. Now, something I might want to do, being a responsible model developer who wants to make sure that I can kick the tires in my own model before I hand it off, is I'm going to run Captum in my own notebook to compute feature attributions with integrated gradients. And so, part of the fun of doing this presentation was I got to play with PyTorch and Captum, which I've been needing to do for a long time. And so it was generally a really cool experience. So hats off to Narina and the team. So here I import integrated gradients. I define an integrated gradient explainer on my model object. I give it the particular feature vector that I'm interested in explaining. And I give it a baseline. That's a sort of a counterfactual against which the attributions will explain the difference. And then I get attributions out. And so what you can see, the output here is you get feature attributions both to the dense vector components as well as to the components of this two-dimensional sequence. So this is telling me how much each of those features is changing the probability of creation of the model. Now, because I'm a little bit handy in my notebook, I choose to draw some nice pictures so that I can understand these numbers a little more easily. So this instrumentation is helping me debug models. It's helping me prune features. It also helps me as a model dev build trust that my models are doing in a sensible way. So you can see here's our dense for some particular example that I grabbed. Red is a feature that's increasing likelihood of churn. Blue is a feature that's decreasing it. This particular customer, the number of products that they have, for some reason, the model thinks that that's a churn risk. Their age is reducing the churn risk a little bit. And then we have all of the attributions in this sequence, and keep in mind the scales are slightly different between these two things. But what you can see there are deposit events that are reducing the churn risk. There are also open accounts, which significantly reduce the churn risk. And in fact, you can see that the more recent open account is more important to the model than the one that is further back in time. So as a developer, it looks to me like the model is paying attention to the right things. Super. But of course, I've got this whole customized notebook environment, installed libraries, data files, transformations, model data. That's not so easy to hand off to other people. And so I want to plug this into Fiddler's MPM platform. And there's plenty of documentation that can tell you the details of how model ingestion works in Fiddler. But there's two key things that I want you to take a look at here. One is I'm going to add a custom explanation in the model schema that defines for the platform what the model looks like. So there's a custom explanation name. I also set it as the default explainer. And then within the model wrapper, so Fiddler requires the user during ingestion to write a little bit of code to adapt the model's interfaces to what Fiddler expects. it's your responsibility then to implement a custom explain function that Fiddler passes a data frame and passes the name of the explanation it wants. And you'll put your code, the same notebook code that I ran there, you'll put in. Get those explanation matrices out. And then there's one last step, is that function needs to return explanations in something called gem. And so this is a bit of technology that we made up. So gem stands for generalized explanation markup. The TLDR is that gem is the connector between your explainer's output and the platform's presentational components. And so this provides the standardization between that heterogeneous portfolio of tools that your organization has and Fiddler's presentation. So I'm going to skip most of this. Essentially, it's just saying that gem is objects that get compiled down into JSON, which is a data serialization format, basically, that allows explanations to be computed. We construct those explanations, the presentational components, in terms of these components: containers, which contain other things, allowing you to nest a hierarchy; simple components, which are categorical features and numerical features, and text components. In the future, there'll be things like image and time series also, but we haven't built that yet. And so when you look at the same model inside of Fiddler's GUI, you're presented with an explanation like this. So attributions are on the right, feature values are on the left. You can see a prediction. You can see how far it is from baseline. Here, these features are interactive. So this allows stakeholders who enjoy interactive exploration. It allows them to fiddle with the feature vectors and see the impact on the prediction and the attributions. You have categories of features. You can see here there's an expand arrow, and we rolled up all of the attributions from inside of that customer history. And then I can drill into these components because I've constructed my presentation of my output that way. So the customer history can be opened up, and you can see how different events in this history are contributing different attributions to the prediction that the model makes. You can even drill in further to see, how the individual features of those events, of a particular event, is driving the model prediction. Super. Okay, so that brings me to the end of what I wanted to talk about. So here I think are the takeaways from this whole session. Narina showed you powerful techniques for explaining complex models. That includes multimodal models, like the ones I just showed you. Captum is an excellent example of a framework-specific interpretability library. Operationalization means making interpretability available to other stakeholders in a standard way across heterogeneous tooling. And then finally, Fiddler is an NPM platform that gives the model developer the option to share their preferred interpretability tools with other enterprise stakeholders. And with that, thanks to everyone out there, and thanks to Narina for doing most of the heavy lifting for this topic.
Thanks to both of you, Nareen and Josh. There were a couple of questions. I think we were able to answer them. So I think we're good there. In less than 30 seconds, we're going to have another tech talk presented by the DoorDash team on how they built their in-house monitoring tool. So stay tuned, and thanks everyone again.